Hello everyone. Now in the previous video we had a look at genetic algorithms. Now genetic algorithms, being a variant of evolutionary algorithms, uses reproduction to pass on genetic material from the one generation to the next. And of course this is done through crossover and mutation. Now mutation allows the genetic algorithm to explore the full range of alleles for a specific gene. And that of course enhances diversity and also combats premature convergence, especially if a specific variant of a gene is not represented by any of the candidates in the population. Now the program I want to demonstrate is called Picture Perfect. Now what Picture Perfect does is you specify an existing image, and then the aim of the program is to evolve that picture. And the only driving force in this algorithm, which is the fitness function of course, is simply a numeric value to say how closely it fits. So let me go through the program, show you the important parts, and then show you the effect that different mutation rates have on the program. Now the first class I want to show you is called this hyperparam. Now what hyperparam does, it just models the hyperparameters of the program. In this case, population size, mutate chance or the probability of mutation taking place, and the extent of the mutation, with how much the algorithm is allowed to modify a gene. And I like to put this in a class of its own because then it makes it easy to do things like grid search and random search or whatever the case may be to find the ideal hyperparameters for the program. So the next class I want to show you is the solution class in the program, and in here we've got a number of members. So the first is target, and this is the actual image we want to evolve. So that's an integer representation of the actual image we want to evolve. And it's important to note that the algorithm does not use target to determine what the pixels should be. It's only used in the fitness function, and in this case it's used because it's a demonstration program. Typically with a real world program or something that solves a real problem, you won't have target, so you'll have to come up with another fitness function to determine how accurate it is. But in this case we've got it available and it's only used in the fitness function. We've got the width and the height of the image, the hyperparameters. Then we've got an array called genes, and this is the actual solution that this specific solution came up with. We want genes to match target somehow. That's the aim. Then we've got fitness, which starts at -1 because we're going to calculate it lazily. We've got a constructor over here that constructs a image for us or a solution for us. Over here we can create a random individual, and you'll see that it literally just creates one where every pixel is a random red, green, and blue. Okay, so that's that part. Then we've got calculate fitness, and this uses target, and this is the only place where target gets used. And this is to basically check how good this solution is. And all I do is, if you look at my code, I go through the entire target array, and I take the current value in genes, I take the blue value, and I subtract the blue value at that same pixel location in target. I repeat that with green and with red. I take the absolute value of all of these because, sometimes the one is lower than the other one, because I want to look at the difference with how much do they differ. I take the absolute, I add them all together, and that becomes the fitness. So all that fitness does is it calculates a single value to determine how good the solution is. And that drives the entire process. And of course, if you do this to the same image, if it's a perfect solution, your fitness will be 0. So this is what's known as a minimization problem. The lower the fitness value is, the fitter the individual is. Next, we've got crossover, and in this case we make use of uniform crossover. Now what's uniform crossover? All that we do is we create an equivalent array in the child, and then we create for every one of those locations, we pick a random value between 0 and 1, and if it's greater than 0.5, we take the gene value from the one parent, and if it's not the case, we take it from the other parent. And that then becomes the genetic material of the child. Now, uniform crossover is useful in cases where the relative positions of genes to other genes does not play a role. Then uniform crossover makes sense. But for problems like, for example, the traveling salesman problem, where you might have a sequence in the genome like 4, 5, 6, and you have to visit the cities in that order, that section is quite optimal. Then you'd rather want to have a look at something like 1 point and 2 point crossover with some added things to avoid the duplicates, but that's a whole different story. But so in this case, we make use of uniform crossover. Then, of course, we've got mutation, and mutation simply takes every pixel or every location in the gene. You'll say I take the blue and the red and the green and the red over here, and I literally just add some small random value to each of those three components. And of course, I only mutate a very small percentage. So I use a for loop that goes from 0 to parameters get mutate chance times width times height. So in other words, I only take, let's say for example, your mutation rate is 1%. I'll only mutate 1% of the genes inside that array. And then of course I set fitness to -1. You have to do that because you've changed values, so the fitness needs to be recalculated. So that's the reproduction operators. Then the last two functions or methods is simply one that returns the current solution and one that's basically lazily calculate the fitness. So if fitness is -1, it means we have to calculate it. So this happens here. Otherwise, we just return it immediately without doing any further calculations. Okay, so now we're finally ready for the main program or the main loop that's going to use the solution class. So in here, we've got the hyperparameters once again, and we've got the array list of solutions, and that's our population. So all the individuals are going to get stored in the population, and that will evolve and change over time. Then we've got the width and the height of the image, and some boilerplate variables like the target image we want to evolve, buffer, which is used for double buffering. Over here we've got the constructor of the picture perfect program, so that starts the whole process. We've got paint that draws it because obviously we want to see how it looks like. Then we've got load target image, and this just loads the image from some source on your local machine. And then we've got two important methods. We've got this get image from array, and we've got get pixels from image. And this basically takes the image, converts it into an array, because obviously a genetic algorithm uses an array. It doesn't use images directly. And the other one converts from your array back into an image so you can display it. Then we've got update, which just basically handles the case when you drag the screen around. And now we're ready for the main algorithm. So the first part, of course, is where we've got init, and init just generates a random population. So you'll see it runs a loop from 0 to get population size in your hyperparameters, and it creates random solutions. So give me a new solution, make it random, and add it to the population. So a complete random set of populations, and of course that looks nothing like the image that you want to evolve. And then we've got the evolve method, and this actually drives the entire algorithm. So we take our image that we want to evolve, and we get the target image array from that, and then we create a random population using that method I've just shown you, and we sort it. So we sort it from best to worst because we're going to make use of rank-based selection. Then we've got a timer, and the reason why I use a timer, it's used in the stopping condition, is because I want to see the effect of mutation, let's say after 3 minutes. So there's a time component. But of course, if you evolve this, you're probably going to stop once you don't see any more improvements or things like that. Then we've got some font settings for some feedback, and here's the main loop. So while there is still time left, we create a new array of offspring. And then while the offspring size is smaller than the population size. So in other words, if your population size is 100, I'm going to create 100 offspring. And then from those 200 individuals, I'll select the best ones. Or I'll select the ones to survive, not necessarily the best ones. Okay, so what happens? We pick two parents, and the way we pick them is very important. So we say math.random times math.random times population size. Now, why math.random twice? This is a quick, cheap trick to ensure that you've got a higher probability to select smaller numbers. In other words, elements that it's in the beginning of the array. So this will make sure that the individuals that are fitter has a higher probability of being selected. Then I just make sure that they're different, because you can't reproduce with yourself. So while P1 is equal to P2, select a new second parent. And then I grab those two parents from the population, and over here I apply crossover. So solution child. So the child is parent 1 crossover with parent 2. So yes, that's where the crossover happens. And then I mutate the child. So the child gets mutated and I add it to the offspring array or offspring array list. So the idea with this method or this part of the method is that it produces an array list of offspring that I can then use in the next generation. Okay, so once I've got all those offspring ready, I simply add it to the population. So my population has now doubled in size. Then I sort them again. You see, I sort them. And in this case, yes, I do take the best half. Then I simply use the method called sublist on the population, and I take the first half, which of course is then a combination of parents and children. So the best half then survives to the next generation. And then over here, I just have some feedback. So that just draws the image. I get the image from the array and I draw it and I paint some fitness values on the screen and so forth. And then I just sleep for 5 milliseconds so that the update buffer or the update thread gets time to draw the screen. And then that's the end of the evolve. Oh yes, very important. Then I just, at the end of that 5 minutes, so the moment this while loop finishes, I simply return the fitness of the fittest individual. And the fittest individual will be the first element in the array. And that's the evolve method. So to bootstrap this program, I've got some, okay, here you see this random hyperparameter tuning. That's just to find the best parameters. We'll discuss that at a later stage. I've got this method called just go, and this is going to do the whole thing. So I initialize the algorithm like this. I specify the image I want to evolve, and I specify my hyperparameters, and then I just get a frame up and running, and I say, where does it start? Oh, here we go. Instance.evolve, and it's not in a headless state because we want to see some feedback, and there it goes. So that's the program. And of course, now let's have a look what happens with different mutation values, which is the actual aim of this video. Now, the first aspect I'd like to explore is what happens if the probability of mutation is set to 0. So over here, here's the hyperparameters. I'm going to set that to 0. Let's just save this. And the population size is 25. So 25 individuals, no chance of mutation. We only have crossover. So let's see what happens if I run this. So there we've got our random image and we've got convergence in under 5 seconds. So you'll see that doesn't really look like an image at all. And the algorithm is unable to find crossover operations between the parents that gives you any kind of further improvement. So that's actually quite bad. And if you look at the fitness value, it's just over 7 million. And given that this is a minimization problem, yeah, that's actually pretty bad. So let's see if we can change that. Now, before we have a look at what happens if we change the mutation rate, let's just increase the population size from 25 to 250 while keeping the mutation probability to 0. So let's see what this increase in population would do to the algorithm. And of course, a bigger population tends to give you more diversity. So strictly speaking, we'll have the fittest individual after some iterations will at least be a little bit better than that 7 million. But yeah, let's see what happens. So 250 individuals. Let's run this algorithm again. So 7 million. It's already below 7 million. So already an improvement of what we had previously. But let's see when this converges. So just under a minute, it seems like we've got convergence that took place. So the algorithm isn't improving any further. So yeah, and we can clearly see there's like a circular object in the middle with a slightly darker, possibly red color. So an increase in your population size definitely adds to the diversity. And now the algorithm has more individuals to pick from to try and find better offspring. But of course, we can still do much better than that. And let me show you how. So we're going to keep the population size to 25. So we're going to decrease the diversity once again But this time, we're going to have a probability for mutation of only 0.5%. So the chance of changing a single gene is 0.5%, which is very, very low. Now, and we're going to keep the mutate extent to 81, which means you can go 40 up or 40-ish down as well. That's the extent of the mutation. So let's see what this does. Now you can clearly see the effect of the mutation already. If you carefully look at the image, you'll see that there's pixels flickering and changing. And of course, that's the variations of the fittest individuals, but each of them has this tiny change. And of course, that drives the algorithm over time to find better solutions. But let's keep this running and see where it ends. I think I'm going to grab a quick coffee while this goes. I've got my coffee, and we don't have convergence yet. It's already been running for over 700 seconds, and you can clearly see that we've got an apple that's trying to get evolved over here. So, and this just shows you the absolute power and the importance of mutation. So even though there's less than 0.5% chance of making a change to a gene, the effect of this cumulatively over time is that you can explore so much more of the search space. And a single number, remember there's just a single number in the fitness function that drives this entire process. And just look at this effect. And we don't have convergence yet, it's still going. So if you leave this for, I don't know, for about some more time, maybe overnight or so, I'm sure that you're going to get something that's incredibly close to the actual image. So yeah, I think that's pretty impressive. And this just shows you the importance of the mutation function as part of the reproduction process. I hope this was useful, and hope to see you in the next video. Keep well and happy coding.